Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello. Good morning. If it's morning there, that is. Welcome to Lesson 4, comparing the ratio method with the parallel method, classwork. Today our goal is to show that the parallel method and the ratio method are equivalent. That is, given a figure in the plane and a scale factor where r is greater than 0, the scale drawing produced by the parallel method is congruent to the scale drawing produced by the ratio method. We start two easy exercises about the areas of two triangles whose bases lie on the same line, which helps show that the two methods are equivalent. So here's the opening exercise. A, suppose two triangles, A, B, C, this one here, and triangle A, B, D, this obtuse triangle, share the same base AB, such that points C and D lie on a line parallel to AB. So AB and CD are parallel lines. Show that their areas are equal. That is, the area of triangle ABC equals the area of triangle ABD. Hint, why are the altitudes of each triangle equal in length? Okay, so I could do this by a construction using a compass, but I'm just going to use a protractor for this. So here's my protractor, and I'm going to rotate it so it's upside down, and I'm going to put the crosshairs, I'm going to make it smaller. Actually, I don't need to make it that much smaller. I don't want it to be non-readable. And I'm going to put the crosshair right on C. Hopefully you can see that. Come on. Right about here. Okay, so my crosshairs are right on C. The 0 line on my protractor is aligned with the line CD, and I'm just going to put a dot down here. That's going to be at the 90-degree mark, which is right about there. Okay, I just marked 90 degrees. Move my protractor out of the way. Go get my ruler way up at the top. Rotate it. Align it with the point C and this dot I created with the protractor. And this is a perpendicular line. So this is 90 degrees. I'm now going to repeat that with D. So I'm going to put my crosshairs of my protractor right on D like so. I'm going to mark the 90 degrees down here, move my protractor, bring my ruler over, align it with D and that point. And this is a perpendicular line to CD as well. And therefore, since AB is parallel to CD, what we have here are 90-degree angles, because they're perpendicular to two parallel lines. Okay. So now I'm going to state what I just did. Okay, so it says draw a perpendicular line to line AB through C. So that's what we just did. Drew a perpendicular line through AB and point C. It's perpendicular to AB, but since AB is parallel to CD, it's also perpendicular to CD. Okay, it says label the intersection of both lines C prime. Okay, so I will label it. That's right here. This point right here is C prime. Then C prime is an altitude for triangle ABC. So remember, an altitude is a line perpendicular to one of the sides going to the vertex of the opposite angle, and that is the altitude of the triangle. Do the same for triangle ABD, get to an altitude of DD prime. So what I'm going to do is put a dot here where it intersected, and that is D prime. So D prime is also an altitude to triangle ABD. Okay? Okay, so now we have a quadrilateral. And the quadrilateral is C, C prime, D prime, D. Here's the quadrilateral. It is a parallelogram. And actually it's a rectangle because the angles are 90 degrees. Therefore, C, C prime equals D, D prime, both of which follow from the properties of a parallelogram. Since C, C prime and DT prime are altitudes of the triangles, we get the area formula for triangles. Remember that area of a triangle is 1/2 the base times the height. So 1/2 AB times CC prime is going to equal 1/2 AB times DD prime, base times height divided by 2. And since ASCC is equal to DD, then 1/2 AB is obviously equal to 1/2 AB. So the area of triangle ABD is going to be equal to the area of the triangle ABC. Okay, that's a pretty cool way of getting about that. Okay, part B says, suppose two triangles have different length bases. AB is obviously shorter than AB prime. So there's two triangles here that lie on the same line. Furthermore, suppose they both have the same vertex, C. So these are two triangles that share a common vertex, but the bases are different. All right. They both have the same vertex, C, opposite these bases. Show that the value of the ratio of their area is equal to the value of the ratio of the lengths of their bases. That is, the area of triangle ABC divided by the area of triangle AB prime C equals AB divided by AB prime. Okay, so the first thing we're going to do is we're going to draw a perpendicular line to AB, line AB. We're drawing a perpendicular line through C down to AB. So I'll take my protractor, I'll rotate it 180 degrees. I'll put the crosshairs right at point C like this, a little bit to the left. There we go. Okay, right about there. And I'm going to put a dot at 90 degrees. My pen, it's right there. Move my protractor, bring my ruler over, line up this point with C, and draw segment C down to AB. And that is C prime, and it is perpendicular to line AB. Okay, so that's what we just did. Draw a perpendicular line to AB through C. So it's off just a little bit, and let me just move it to the left. Right there, that's about good, right there. All right, so that's step one. Step two, what do we need to do? We need to say what that means. So that means that C prime is an altitude for both triangle ABC and AB prime C. It is an altitude for the two triangles. Okay, then we can just state the obvious. Hopefully it's obvious to you. If not, it will start getting easier by practicing. So if we have an area formula, if we say the area of triangle ABC is 1/2 AB times CC prime, and we divide that by the area of triangle AB prime C, that will equal 1/2 AB prime times C prime. So let me just point out what's going on here. Area of triangle ABC is right here. That's triangle ABC right there. And triangle A, I'm going to go outside here, by the way. Triangle AB prime C is right here. Okay, so where'd my green side go? My green side's gone. All right, let me do this again. I'm missing a side of my green triangle. So that's right here. Okay, so now hopefully you can see the two triangles. One's green, one's blue. So what we're taking is a triangle ABC. The area of triangle ABC equals 1/2 AB times CC prime. 1/2 the base times the height. Then the blue one is down below. Well, 1/2 AB prime times CC prime, the height, is going to equal AB over AB prime. And how does that happen? Well, anything divided by itself is 1. So 1/2 divided by 1/2 cancels. CC prime divided by CC prime cancels, leaving AB over AB prime. And that's what we just proved. Okay, page 2 brings us to a discussion. It says, to show that the parallel and ratio methods are equivalent, we need only look at one of the simplest versions of a scale drawing, scaling segments. First, we need to show that the scale drawing of a segment generated by the parallel method is the same segment that the ratio method would have generated, and vice versa. That is, the parallel method yields the ratio method, and the ratio method will yield the parallel method. The first implication above can be stated as the following theorem. Parallel ratio method, or rather parallel to ratio theorem. Given segment AB, right here, and point O, right here, not on line AB, construct a scale drawing of AB with scale factor R greater than 0 using the parallel method. Let A prime equal the dilation about O of R, that's your dilation R, ratio A. So all they're saying here is A prime is A dilated out from O. And let L be the line parallel to AB that passes through A prime. Okay, so they're just naming this line right here, L. Let B prime be the point where ray OB intersects that line L. Then B prime is the same point found by the ratio method. That is, B prime equals the dilation from O of ratio of B out to B prime. Okay, so that's all they're saying. Proof. We prove the case where R is greater than 1. The case where R is between 0 and 1 is the same, but with a different picture. Construct two line segments, B, A prime. So then they tell you to draw a line segment from B diagonal over to A prime. So that was this drawing. We just drew this line over here, and that's going to form the purple triangle. Okay, and A, B prime, so that'd be from here up to here, forming the yellow triangle, and yellow and the purple makes this green intersection. To form two triangles, B, A, B prime, and B, A prime, the purple triangle. So this one's purple and this one's the yellow one, labeled as T1 and T2, respectively in the picture below. So there's the picture. Okay, so we're continuing this proof on page 3. Now we're going to say the areas of these two triangles are equal. Area of triangle T1, which was the purple triangle, I believe. Let me go back. They aren't labeling it here for some reason. No, T1's the yellow one. So the area of this yellow triangle, this one here, is equal to the area of T2, the purple one, by exercise 1. Why? Label triangle OAB by T sub 0. So this is T, they also would say T naught, okay? Whenever you see a T with a subscript of 0, you can say T sub 0 or T naught. Okay, so that's triangle T naught, the white one. Then area triangle OA prime B, OA prime B, which is right here, equals the area of OB prime A, this triangle over here. Okay. And the reason is OA prime is our base and B is our altitude in this triangle. But over here, OA is our base and B prime is our altitude. So if you take area of triangle OAB, which is OA prime B, which is this triangle down here, it equals the area of T naught and T2. So it equals the area of the white plus the purple. Okay. Area T naught plus area T1 is the area of this. This is T naught, this is T1. So let me label that because they aren't labeled here, just to make sure. The yellow one is T1. So I'm going to label that so we have it. This little piece here is T1 and the purple is T2. So this is T2, T1, and they overlap with that green. Okay. So since the area of O, A prime B, this equals T naught plus T2, and area of T naught plus T1 it's equal to that as well, then it also equals the area of O, B prime A, which is this. Therefore, area of triangle OA prime B, right here, is equal to OA prime over OA. And that was from the prior proof we did, because 1/2 of, we're doing the area and then things cancel. And then also area of OB prime A over area T naught, which is OBA. The 1/2s cancel and the altitudes are what's left. So OB prime is over OB. So it's a ratio of the whole thing divided by the ratio of the original. We're shorter. Since area of OA prime B equals area of OB prime A, we can equate the fractions. OA prime over OA equals OB prime over OB. And we can do that by substitution. Since R is the scale factor used in dilating OA to OA prime, we know that OA prime over OA equals R. Therefore, OB prime over OB equals R, or OB prime equals R times OB. So what they did here was they multiplied both sides by the denominator, a little algebra trick there. And that's how they got OB prime equals R times OB. This last equality implies that B prime is the dilation of B from O by a scale factor R, which is what we wanted to prove. Next, we proved the reverse implication to show that both methods are equivalent to each other. Okay, so here on page 4, we're going to do the other direction. We're going to prove that going from ratio to the parallel theorem. So given AB, let me label these up while I do this. We'll color code as we go. So it says given AB, right here. Whoops, what happened to my command that I asked for? Do-de-do. given AB, and point O. So I'm going to put a red dot at point O. Those are our givens. Not on AB, obviously. O's here, AB's over here. O is not on AB. Construct a scale drawing, A prime, B prime, of AB with a scale factor R greater than 0 using the ratio method, i.e. find A prime, which is a dilation from O of some ratio of A, and B prime, a dilation from O of some R ratio of dilation of B to get to B prime, and draw A prime, B prime. Then B prime is the same as the point found using the parallel method. Okay, so now they're saying here, if this is OB and we dilate it by a ratio R, then OB times R is B prime. And also OA times a dilation of R from O gives us OA prime. Proof. Since both the ratio method and the parallel method start with the same first step of setting A prime equal to the dilation from O of some ratio of A, the only difference between the two methods is how the second point is found. If we use the parallel method, we construct the line L parallel to AB. So they're calling this line L right here. This line here. So it's going to be parallel to AB. So you see the parallel markers. Okay. And passing through A prime. And label the point where L intersects OB by a C. So there they did that right there. Then B prime is the same as the point found using the parallel method if we can show that C equals B prime. So we want to prove that this C is equal to B prime. Okay, so by the parallel to the two ratio theorem, we know that C, this C, equals a dilation of B from the point O of a ratio R. That is, C is the point on the ray OB such that OC equals OB times that R. But B prime is also the point on OB such that OB prime equals R times OB. Hence, they must be the same point. The fact that the ratio and parallel methods are equivalent is often stated as the triangle side splitter theorem. Okay, kind of like a good joke. The side splitter. To understand the triangle side splitter theorem, we need a definition. Side splitter, a line segment CD, line segment, which is right there. That's line segment CD. Please cooperate. Okay. Line segment CD is said to split the sides of OAB. So it's going to split the sides of this big triangle proportionally if C is a point on OA and D is a point on OB. And OA over OC equals OB over OD. So they're setting up a proportional ratio. The whole over the part equals the whole thing over the part. Or equivalent, OC over OA equals OD over OB. So you can either say the whole thing over the piece equals the whole thing over the piece, or the piece over the whole thing equals the piece over the whole thing. So if we're going to take the inverse of both fractions, then they're both still equal. So what they're saying is if I had A over B equals C over D, then I can flip them and say B over A equals D over C. Okay, and that is true because if you cross multiply, you get AD equals BC and AD equals BC. Okay, so if that happens, then we call the line segment CD a side splitter. So triangle side splitter theorem says a line segment splits two sides of a triangle proportionally. There's the key right there, proportionally. Proportionally. If and only if it is parallel to the third side. So that only happens if AB is parallel to A prime, B prime. So it's a restatement of the triangle side splitter theorem. So it says in triangle O, A prime, B prime, the big triangle, AB splits the sides proportionally, i.e. OA prime over OA equals OB prime over OB. If and only if A prime, B prime is parallel to AB. Page 5 brings us to the end of lesson 4. Review the lesson summary and go to your problems.